Imagine this. Traveller, you didn't arrive here by accident. Something in the quiet geometry of the cosmos guided you toward a question that won't let humanity sleep. What if an object drifting silently between Mars and the Sun is not a comet at all, but a fragment of another star, passing too close? Consider the odds a 1 in 20,000 trajectory, brushing past 3 worlds, timed with the single week our telescopes go blind. A light that blinked once and was gone, a whisper hidden in background radiation, and now it waits. Stay a while, traveller. The appearance of the alleged October 21st, 2025 leaked image of 3I Atlas introduced a new layer of complexity into the study of this interstellar object, not because it provided confirmation of any extraordinary hypothesis, but because it highlighted the persistent tension between instrument limitations, observational bias, and the human inclination to interpret ambiguous data as intentional structure. What circulated online was a compressed low-fidelity frame attributed to an unnamed Japanese space tracking facility, showing an elongated luminous form with what appeared to be evenly distributed points of brightness along a narrow axis. Unlike the diffuse optical signature expected from an active comet near the Sun, where sublimating volatiles scatter instant sunlight into a soft asymmetric glow, the object in this frame appeared sharply bounded with no discernible coma, no visible dust emission, and a luminosity profile that seemed unusually coherent for a natural fragment of ice and rock undergoing rapid solar heating. These characteristics motivated widespread speculation, yet from a scientific perspective, each feature demands careful evaluation before meaningful interpretations can be drawn. To assess the validity of the image, it is essential to place it within the broader context of 3I Atlas's observed behaviour. 3 months of verified telescope data have consistently supported the classification of the object as an interstellar comet, exhibiting atypical but not unprecedented chemical signatures. Spectroscopic measurements from Hubble JWST and ground-based observatories have identified strong carbon dioxide release an unexpectedly high nickel signal and an unusual suppression of typical organic bands. These factors complicate its categorization, but remain within the possible chemical diversity of objects formed in non-solar environments. Furthermore, the observed light curve and dust production rates align with natural models of outgassing, modulated by rotational cycles and anisotropic surface composition. In short, all confirmed data remain consistent with a rare but natural cometary body. The leaked image, however, appears inconsistent with those established characteristics. This inconsistency alone suggests artifact rather than revelation. Observing objects near the Sun is intrinsically error-prone due to extreme photon flux sensor blooming, atmospheric diffraction for ground-based imaging, and thermal noise. Under such conditions, faint moving targets can elongate or segment into false structures when detectors saturate or when multiple exposure frames are improperly integrated. If the image originated from automatic satellite tracking software, even minor misalignment during frame stacking can create the illusion of irregularized luminous nodes, pixel clusters, not physical lights. Without access to the metadata normally accompanying scientific images, exposure times instrument filters, pointing vectors, thermal calibration, and starfield identifiers, the image cannot be evaluated through the standard verification pipeline. Its scientific value, therefore, is effectively zero until provenance is established. Another factor influencing public interpretation is the timing of the image release. 3 Atlas is currently approaching perihelion, a region where Earth-based telescopes suffer complete observational blackout due to solar interference. This creates a natural interval of uncertainty. For approximately 1 week, the object cannot be observed by optical instruments positioned near Earth. Such intervals historically invite speculation, but they do not imply intentionality. The orbital mechanics involved are well understood. Hyperbolic interstellar objects approach the Sun on trajectories determined by their incoming velocity vector and the gravitational potential of the solar system. The geometry that places 3I Atlas behind the Sun relative to Earth is a predictable outcome of these dynamics and not meaningful evidence for anomalous behaviour. Still, the appeal of the image persists because it appears to contradict the expected appearance of a comet at this stage of solar approach. Under strong solar heating, comet nuclei typically become more obscured, not less, as the coma thickens and dust production increases. A sharply defined linear structure would therefore be unexpected if real. This is precisely why the scientific default remains skeptical. Extraordinary morphology requires extraordinary imaging conditions, and nothing in the metadata less image indicates that such conditions were present. It is far more plausible that the object's perceived structure reflects sensor saturation motion, blur digital, overcompression, or selective enhancement by the uploader. The comparison to the independent capture by amateur astronomer Tiago Dobsoni and Power requires similar caution. His observation, a stacked image taken under non-ideal conditions, likewise suggested an elongated white core with little visible coma, but his own technical notes highlight the limitations of solar-adjacent imaging. Monochrome detectors saturate readily. Atmospheric seeing distorts faint targets, and aggressive stacking necessary to extract faint signals tends to smear moving objects along their motion vector. The apparent agreement between the two images can thus be traced to identical observational constraints, not necessarily to an underlying physical structure. In the broader scientific framework, the responsible interpretation is that both images reflect the challenges of high contrast near solar imaging, rather than the discovery of a structured extraterrestrial probe. The confirmed dataset spectroscopy photometry astrometry supports a natural object following a predictable hyperbolic trajectory, even if some elements of its chemistry and brightness curve require refinement to existing comet models. Nothing in the verified observations indicates artificial lighting, manufactured geometry, or non-gravitational propulsion signatures beyond those explainable by anisotropic outgassing. Yet the value of the leaked image is not entirely null. Scientifically, it serves as a reminder of the importance of rigorous provenance calibration and data transparency in astronomical research. Sociologically, it demonstrates the public's hunger for definitive answers in a domain characterized by uncertainty. The interstellar nature of Three-Eye Atlas already places it in an exceptional category, and exceptional objects attract exceptional speculation. But science advances not through speculation, but through the slow accumulation of reproducible measurements. As the object enters solar conjunction, the scientific community waits for its re-emergence in early November, when new spectroscopic and astrometric data will allow researchers to determine whether its trajectory remained consistent with a purely gravitational path or whether any measurable deviations occurred during its time behind the Sun. Until those measurements are available, the only scientifically responsible position is cautious neutrality. An extraordinary claim cannot be supported by an unverifiable image. As Three-Eye Atlas entered the final days before solar conjunction, scientific attention shifted from morphology to dynamical behaviour. While public discourse focused heavily on the ambiguous imagery discussed in Part 1, researchers were primarily concerned with whether the object's trajectory exhibited any measurable deviations from a purely ballistic path. Non-gravitational forces are common in comets produced by outgassing jets that modify the acceleration vector by small but detectable amounts. These perturbations, when modelled appropriately, yield insights into nucleus-shaped rotational state and volatile distribution. For Three-Eye Atlas, any such deviations carry heightened significance, not because they suggest artificiality, but because they reflect compositional and structural properties that differ from solar system-borne comets. Available data from early October indicated mild non-gravitational acceleration, consistent with carbon dioxide-driven outgassing. Spectroscopic observations from JWST identified CO2 as the dominant volatile, a composition unusual but not unprecedented among interstellar objects. The challenge lies in quantifying how this outgassing translates into changes in orbital parameters. For natural comets, the non-gravitational acceleration typically ranges from 10.8 to 10.6 MES2, depending on activity level. Preliminary fits for Three-Eye Atlas suggest values near the lower end of this range. If confirmed, these values fall well within the expected spectrum for a weakly active comet approaching perihelion. The question often raised in speculative interpretations is whether any trajectory changes could indicate intentional maneuvering. Scientifically, this possibility must be dismissed unless the magnitude or direction of the acceleration fundamentally contradicts known cometary physics. Artificial propulsion would require either sustained thrust signatures or abrupt velocity shifts incompatible with mass loss models. No such evidence has appeared in any verified astrometric dataset. The object's path conforms to predictions from July through October, with deviations explainable by non-uniform surface heating. Thus, the dynamical behaviour remains entirely consistent with a natural origin. Another significant consideration involves the thermal environment near perihelion. As 3I Atlas approaches its closest distance from the Sun, the incident solar flux increases rapidly. For a perihelion distance near 1.4 AU, solar radiance roughly doubles compared to its value at 2 AU. This change in thermal input influences the sublimation rate and can cause abrupt brightness fluctuations. Several observing teams reported steep increases in apparent magnitude during the first half of October, followed by minor declines. Such variability is typical of comets undergoing rotational modulation and heterogeneous surface activation. The absence of explosive outbursts or fragmentation events suggests that the nucleus possesses sufficient cohesion to withstand thermal stress. This observation indirectly supports the hypothesis that the object is comparatively large, possibly exceeding several kilometers in diameter, which would align with earlier mass estimates derived from coma brightness. It is worth noting that speculative interpretations often highlight the lack of a persistent, well-defined cometary tail in available imagery. However, the absence of a tail is not anomalous. Tail formation depends on dust grain size, distribution, ejection, velocity, and radiation pressure. An object dominated by volatiles with low dust content can produce a gaseous coma, with minimal dust leading to weak or undetectable tail structures. This phenomenon has been observed in multiple CO2-dominated comets within our solar system. In the case of 3I Atlas, the spectroscopic evidence strongly favours a gas-rich dust, poor composition making the weak tail entirely consistent with physical expectations. The forthcoming period when the object re-emerges from behind the Sun will provide critical data for testing these models. If the brightness evolution post-perihelion reflects typical insolation-driven decline, researchers can refine thermal models and estimate active surface fractions. Conversely, if significant discrepancies arise such as asymmetrical jetting or changes in rotation period, additional revisions to the comet's physical model may be required. None of these scenarios implies anything non-natural. They simply reflect the complexity of modelling interstellar material with unknown primordial conditions. Another aspect worth examining is the statistical argument surrounding the trajectory. Much attention has been given to the improbability of its near alignments with multiple planets. These numerical arguments, while compelling at first glance, often rely on simplified assumptions about the distribution of interstellar trajectories, neglecting gravitational bias, observational selection effects, and the enhanced detectability of objects transiting near the ecliptic plane. Interstellar bodies entering the solar gravitational well are more likely to be observed if they pass through regions intensively monitored by survey telescopes, which overwhelmingly focus on the ecliptic. Thus, observational bias skews detections toward low-inclination orbits. When these factors are correctly integrated, the probability of observing an object with 3I Atlas's trajectory increases substantially, undermining claims of statistical anomaly. In addition, the comet's chemical profile has been central to speculation, especially the strong nickel signature. Yet nickel emission lines, while uncommon, are not physically incompatible with models of cometary nuclei formed in metal, rich protoplanetary disks. The detection of nickel tetracarbonyl has been discussed in media narratives, but there is no consensus in peer-reviewed literature confirming this compound's presence. The known measurements can be explained by atomic nickel emission and do not require synthetic or engineered chemistry. This exemplifies the broader issue. Ambiguous spectral data, when removed from scientific context, can be misinterpreted as evidence of artificiality, even though mundane explanations exist. Ultimately, the anticipation surrounding 3I Atlas's perihelion is not due to credible signs of non-natural behaviour, but to the rare opportunity to study an interstellar body under solar heating. Its composition, structural integrity, rotational dynamics, and non-gravitational acceleration will provide crucial constraints on models of planet formation beyond the solar system. The true scientific value lies not in speculation about extraterrestrial engineering, but in expanding the empirical foundation for understanding the diversity of interstellar objects. When the object emerges from behind the Sun, renewed astrometric and spectroscopic measurements will determine whether it adhered to its predicted track. A consistent trajectory will reinforce natural models. A measurable anomalous deviation, while unlikely, would require re-evaluation of sublimation, physics, or surface heterogeneity. Either outcome enriches our knowledge. In science, uncertainty is not a void to be filled with extraordinary assumptions, but a transitional state preceding improved understanding. 3I Atlas is not a riddle to be solved by conjecture. It is a data point rare, valuable, and scientifically illuminating regardless of what the unverified images may appear to show. As the discussion around 3I Atlas progressed, attention turned increasingly toward the imagery circulating in both professional and amateur communities, while the scientific consensus emphasized caution. Certain morphological claims demanded closer examination, not because they indicated artificiality, but because they highlighted how observational conditions and image processing techniques can distort interpretation. The leaked clip described in earlier sections portrayed an elongated rod-like structure with discrete luminous nodes along a central axis. To evaluate such claims rigorously, one must begin with the physics of astronomical imaging, which governs how light interacts with detectors, atmospheres, and optical systems. When observing faint objects near intense light sources such as the Sun, images are overwhelmingly shaped by scattering, diffraction, and sensor noise. The point spread function PSF of any telescope defines how a point source of light is distributed across the detector, and under solar-adjacent conditions the PSF broadens dramatically. Diffraction-induced elongation can produce linear structures even when the true object is compact and unresolved. Furthermore, deconvolution algorithms, often applied by amateurs attempting to enhance clarity, introduce ringing artifacts, symmetric patterns, and false edges. These mathematical transformations amplify noise and can create the illusion of evenly spaced luminous nodes. Thus, the visual symmetry described in unverified media cannot be treated as intrinsic morphology. A similar issue arises with the perception of uniform luminosity. A cometary coma, when compressed through aggressive contrast enhancement, can appear as a smooth sheath of light. The human visual system is predisposed to detect geometric patterns even when none exist, a cognitive bias known as pareidolia. In the context of faint astronomical targets, pareidolia can transform random gradients into structured features. Such misinterpretations are not unique to 3I Atlas. They have occurred repeatedly in historical observations, including earlier images of 1 Dyes Oumuamua and 2I Borisov, both of which were periodically described as anomalous due to image processing artifacts rather than physical properties. Moving from artifacts to physics, natural processes can also produce brightness patterns that superficially resemble artificial structures. Cometary surfaces are not uniform. Localized jets from volatile-rich fractures can create discrete bright regions along the nucleus. If the rotational axis is oriented near the observer's line of sight, multiple active areas may appear nearly aligned. These jets emit dust and gas that scatter sunlight efficiently at specific phase angles. Forward scattering, particularly strong when the object lies between the observer and the Sun, can intensify these bright spots, making them appear more discrete than they actually are. Forward scattering enhancement is a well-documented phenomenon, and many comets exhibit unexpected brightness asymmetries for precisely this reason. In the case of 3I Atlas, the reported absence of a broad diffuse coma in certain images has been used to argue for non-natural morphology. Yet this interpretation neglects the effects of filter selection. Narrowband images isolating CN or NII emission significantly suppress continuum dust scattering, yielding a more compact appearance. Under such filters, active regions dominate the frame while the dust envelope becomes nearly invisible. Thus, images taken in emission line filters can resemble luminous nodes against a darker background, a consequence of spectroscopy, not structure. In addition to optical artifacts, atmospheric turbulence plays a crucial role. Amateur solar imaging often relies on high magnification setups pushing resolution limits. Thermal gradients above ground surfaces produce refractive instabilities, known as seeing which distort incoming wavefronts. Even with lucky imaging techniques capturing thousands of frames and stacking only the sharpest residual distortions can mimic linear forms or clustered bright regions, the Thiago-Dobsonian frame referenced earlier presents such characteristics a grainy noise-dominated image, where faint structures blur into elongated shapes. Scientific evaluation emphasizes that these are signatures of atmospheric interference rather than physical features. Beyond imaging considerations, there is also the question of spectral consistency. If discrete light sources existed along a rigid structure, they would produce narrowband emission distinct from known cometary molecules. No such anomalous lines have appeared in any verified dataset. All confirmed spectra exhibit molecular CN atomic nickel and common fragmentary emissions in the near-ultraviolet and visible bands consistent with volatile-driven coma chemistry. Notably, atomic nickel emission arises naturally from photodissociation of volatile carbonyl compounds, not from thermal radiators or engineered lighting arrays. This spectral evidence strongly supports the natural hypothesis. Consider also the rotational dynamics of the object. A rigid elongated body with luminous nodes would exhibit periodic variations in brightness, correlated with rotational phase. These modulations would appear in photometric light curves collected over several nights. Observers have reported mild variability in the brightness of 3I Atlas, but the variations align with the models of irregular partially active nuclei rather than structured artificial geometry. Photometry shows broad, smooth changes consistent with shifting jet activity, not the regular pulsed modulation expected from aligned point emitters. The claim of symmetry requires further scrutiny. Natural bodies rarely display perfect axial regularity, whereas optical systems often impose symmetry through PSF reflection. Diffraction spikes, caused by telescope support struts, generate symmetric arms around bright sources. If the nucleus or an inner region of the coma saturates the detector, blooming effects can create false linear streaks. These streaks propagate along pixel columns, producing an appearance highly reminiscent of engineered structures. The combination of blooming diffraction and post-processing can easily yield images misread as artificial. Theoretical models of comet morphology reinforce this interpretation. Multi-jet comets such as 103P, Hartley 2 and 67P Churyumov-Gerasimenko have exhibited structured features under specific illumination and viewing geometries. When captured under low phase angles or high contrast processing, their jets appear as discrete luminous nodes along a central axis. This resemblance to artificial constructs highlights the difficulty of morphologically classifying low-resolution imagery. In the absence of high-fidelity resolved imaging unavailable for 3I Atlas, scientific caution requires avoiding conclusions drawn solely from shape. Finally, the broader astrophysical context must be acknowledged. Interstellar objects travel through diverse stellar environments before encountering the solar system. Their surfaces accumulate irradiation effects, microfractures, and compositional gradients unlike those of local comets. These differences can create unfamiliar visual signatures without implying artificiality. Morphological novelty is expected from interstellar material. Interpreting novelty as intention is scientifically unwarranted. In summary, the morphological claims surrounding 3I Atlas can be reconciled with well-understood optical physics, atmospheric distortion, and natural cometary processes. No verified measurement supports the existence of rigid structures, luminous nodes, or engineered symmetry. The available evidence, when evaluated through established astrophysical principles, reinforces the natural object hypothesis. As 3 Atlas continues toward perihelion and through the solar conjunction interval, the scientific community remains guided by data rather than impression, aware that unresolved imagery often reflects the limitations of observation more than the nature of the object itself. As morphological interpretation settled into a clearer scientific context, attention shifted toward the temporal and dynamical framework that governs our understanding of 3I Atlas. In astrophysics, timing is never incidental. It shapes the boundaries of what can be measured and what inevitably escapes observation. For an interstellar body accelerating toward the Sun, this relationship between orbit illumination and observational geometry becomes central. The approach of 3I Atlas toward its perihelion has created precisely such a convergence, one where the physics of motion, the limitations of instrumentation, and the contingencies of celestial alignment intersect. The object's hyperbolic trajectory signals an origin beyond the solar system, its path shaped by the gravitational field of the Sun rather than bound to it. As 3I Atlas descends inward, its velocity increases, rapidly compressing the timeframe available for detailed observation. Objects passing near the Sun do not linger. Their acceleration shortens opportunities for spectroscopic and photometric monitoring, forcing astronomers to rely on brief observational windows interspersed with unavoidable gaps. The most significant of these gaps is the solar conjunction interval, during which the Sun's glare overwhelms Earth-based telescopes. From our vantage point, the object becomes lost behind a curtain of scattered light. This conjunction occurs almost exactly as 3I Atlas reaches perihelion, a coincidence that restricts our ability to observe the object during the phase in which its physical properties are likely to change most dramatically. Near perihelion, volatile, rich surfaces heat, rapidly jets become more active, and the comet's coma can evolve within hours. Yet none of these behaviours can be directly monitored from Earth when the object is angularly close to the Sun. This is not unique to 3I Atlas. It is a recurring challenge for observers studying sun-grazing or near-Sun comets, but for an interstellar object whose properties remain intrinsically more uncertain, the blackout window carries particular scientific weight. It temporarily removes the only line of direct observation, leaving researchers to extrapolate behaviour based on pre-perihelion trends. Once solar glare dominates ground-based observatories, effectively lose access. Space-based platforms offer limited alternatives. Instruments such as SOHO and STEREO possess coronagraphs capable of imaging regions near the Sun, but their design suits large-scale solar structures rather than faint, fast-moving interstellar objects. These spacecraft might detect broad brightening or gross motion, yet their spatial resolution is insufficient to provide morphological detail or fine spectroscopic signatures. For 3 Atlas, any conjunction-era data from these missions will function primarily as confirmation that the object persisted through perihelion, not as a diagnostic tool for refining physical interpretation. The real testing ground for scientific hypotheses emerges after conjunction ends. Post-perihelion astrometry, precise measurements of the object's position over time, allows researchers to refine the orbital solution. Small deviations from expected positions can reveal the magnitude and direction of non-gravitational forces acting on the object. Such forces, typically arising from asymmetric outgassing, are well documented in cometary science. The venting of gases acts like a natural thruster, applying subtle accelerations that shift the orbit slightly. These effects are usually random in direction and small in magnitude, tied to the distribution of volatile rich regions on the nucleus. For 3I Atlas, spectroscopic indications of active volatiles suggest that similar mechanisms are likely to operate during and after perihelion. If the post-conjunction trajectory matches pre-conjunction predictions within expected uncertainties, the natural object model strengthens. If discrepancies appear, they must first be evaluated through thermophysical models. Rotation, surface, heterogeneity, fracturing and thermal lag can all drive asymmetric gas release. Only if such natural explanations fail would more exotic interpretations gain relevance. In this sense, the trajectory becomes a crucial arbiter, not because it hints at intention, but because it tests the completeness of our physical assumptions. Thermal behaviour near perihelion further informs these assumptions. As 3I Atlas absorbs solar radiation, surface and subsurface temperatures rise, activating volatile species such as carbon monoxide and carbon dioxide. These compounds sublimate at lower temperatures than water ice, meaning an interstellar comet enriched in these volatiles may become active at greater distances and in unfamiliar patterns. Spectroscopic detection of atomic nickel, unusual but explainable through photochemical pathways, illustrates the diversity of reactions that can occur under increased solar illumination. Photodissociation of metal-bearing carbonyl compounds can produce metal atoms without requiring extreme heat or artificial processes. Thus, the perihelion environment provides the conditions under which complex but natural chemistry becomes visible. This chemistry in turn shapes the morphology of the coma. Observations of a sunward jet or anti-tail illustrate how geometry and thermal asymmetry interact. A jet directed toward the sun does not signify motion toward it. Rather, the jet disperses away from the nucleus, but appears sunward because of projection effects. When the observer's line of sight aligns with the jet's direction, it manifests as a narrow, bright extension. Such features have been documented in multiple comets, particularly those with confined active regions. The persistence of a sunward structure in 3 Atlas suggests that a stable fracture, or volatile-rich vent on the nucleus, dominates sublimation, an interpretation consistent with both spectroscopic and photometric behaviour. Instrumental limitations continue to complicate analysis. Even high-quality amateur solar observations such as the Thiago-Dobsonian capture operate near the limits of what consumer-grade equipment can achieve. Solar glare, atmospheric turbulence, and thermal distortions impose significant constraints. Noise amplification, gain-induced artifacts, and chromatic aberrations can create illusory structures or exaggerate real ones. Professional astronomers therefore treat such data carefully, not dismissing it, but contextualizing it within known imaging constraints. Isolated frames provide hints, not conclusions. The broader scientific methodology reinforces this cautious approach. Reliable interpretation arises not from any single frame spectrum or dataset, but from the convergence of multiple lines of evidence. For 3I Atlas, the accumulated data trajectory consistency, volatile-driven emissions, thermally induced activity, and morphology explainable by geometry and image processing continues to favour the natural model. While uncertainties remain, they lie within expected ranges for an interstellar comet, rather than outside them. Thus, as Theresa Stereo-Atlas completes its solar passage, the scientific narrative remains one of continuity, an object shaped by processes familiar in cometary physics, modified by its interstellar history, and observed under challenging conditions. The conjunction window delays clarity, but does not obscure the underlying physical principles guiding our interpretation. As the discussion of observational geometry and thermal behaviour matured, scientific attention turned toward the methodological contrast between natural explanations and claims of artificial origin. This contrast is neither rhetorical nor philosophical. It is rooted in the epistemic structure of astrophysics, which demands that extraordinary interpretations be supported by equally extraordinary evidence. In the case of 3I Atlas, the question is not whether artificiality is impossible, but whether the available data require it. To answer that question, one must examine how natural mechanisms account for the object's observed properties, and equally important, what kind of evidence would be necessary to exclude them. The first natural mechanism is the behaviour of volatile-driven outgassing. Comets both interstellar and solar possess heterogeneous surfaces shaped by microfractures, uneven irradiation, and compositional layering. When such surfaces heat, sublimation occurs non-uniformly, producing jets that expel gas and dust with measurable force. These jets evolve, rapidly change direction depending on rotational phase, and often cluster around structurally weakened regions. For 3I Atlas, early spectral detections of carbon-based molecules and atomic nickel indicate a chemically active nucleus undergoing photothermal reactions. This is entirely consistent with cometary dynamics, particularly for an object with extended exposure to interstellar radiation prior to entering the solar system. The morphological anomalies, such as the absence of a long dust tail or the presence of a compact sunward feature, are compatible with scenarios in which the dust production rate is low grain, sizes are dominated by larger particles, less affected by solar radiation pressure, or the observer's perspective suppresses the visibility of extended structures. Solar phase angle plays a crucial role. Small particles scatter most efficiently when illuminated from behind, which enhances the apparent brightness of the coma in some geometries and diminishes it in others. Thus, the limited visibility of a tail is not surprising near conjunction, where sunlight alignment produces harsh contrast gradients. Another key natural mechanism concerns the evolution of interstellar objects over long timescales. Unlike solar system comets, which originate from reservoirs such as the Oort cloud or Kuiper belt, interstellar comets have endured radiation environments, stellar winds, and micrometeoroid bombardment from multiple star systems. These conditions may alter surface composition, weaken structural integrity, and produce volatile distributions uncommon in locally formed bodies. For example, A comet with depleted water content but enriched carbon monoxide or carbon dioxide would display different activation thresholds and sublimation patterns. This aligns well with reported spectra of 3Som Atlas, which indicate relatively low water signatures, even as carbon-based volatiles dominate near perihelion. Spectroscopic evidence is particularly informative. If a body possessed engineered components or artificial illumination, one would expect narrow-band emission lines, not associated with known molecular transitions or thermal continua inconsistent with passive heating. Yet spectroscopic surveys from professional observatories consistently identify natural molecular signatures. Cyanide, a common species in cometary environments, appears prominently. Nickel emission, while unusual, is explainable through the thermal decomposition of carbonyl compounds under intense ultraviolet radiation. In all datasets, the distribution of detected lines reflects chemical processes known to occur in highly irradiated cometary comae. The question of morphology therefore demands a careful separation of physical structure from observational representation. Low-resolution imaging, especially under solar-adjacent conditions, is susceptible to distortions that can mimic structured geometries. When small bright regions along an irregular nucleus are blurred by atmospheric turbulence, or enhanced through deconvolution algorithms, they may appear as aligned luminous nodes. This illusion is strengthened by the cognitive tendency to impose linear order on stochastic patterns. Thus, the visual appearance of 3I Atlas, as a rod-like or spindle-like form, arises not from intrinsic structure, but from the interaction between light heat and instrumentation. One of the most powerful arguments supporting natural interpretations lies in the predictability of gravitational motion. For a body to be considered artificial, it would need to demonstrate deviations from its expected trajectory that cannot be explained by non-gravitational forces or measurement uncertainty. Cometary non-gravitational acceleration is well understood. It depends on the momentum carried by sublimating gases and varies as the nucleus rotates. These effects are detectable but small. If 3I Atlas exhibits post-perihelion motion that fits within the range allowed by outgassing models, then gravitational and thermophysical processes account for the observed behaviour without the need for speculative propulsion hypotheses. Additionally, rotational dynamics offer crucial insight. Irregular bodies exhibit characteristic light curve signatures, variations in brightness caused by changing cross-sectional area as the nucleus rotates. Artificial bodies, by contrast, often display rotational stability or periodicity inconsistent with chaotic tumbling. Early photometric data for 3I Atlas, though limited, indicate variability consistent with a rotating natural object. The absence of sharp periodic modulation suggests that luminous regions are diffuse and not tied to engineered components. Understanding what evidence would be required to reject natural explanations is equally important. Definitive indicators of artificiality would include sustained non-gravitational acceleration, inconsistent with sublimation, spectral features unrelated to known molecular transitions, thermal emissions exceeding predicted values based on solar heating, or resolved imaging revealing geometric symmetry beyond what natural processes produce. None of these conditions have been met. Observations remain consistent with a comet undergoing thermal evolution and volatile-driven activity. Furthermore, the lack of strong infrared emissions argues against the presence of active thermal management systems, which would be necessary for any spacecraft operating near the Sun. Similarly, no narrow-band radio emissions or structured signals have been detected despite monitoring by radio observatories capable of identifying artificial transmissions. The silence in these domains reinforces the view that 3I Atlas behaves as a natural astronomical body rather than as an engineered probe. The scientific value of 3I Atlas lies not in its potential artificiality, but in the opportunity it provides to refine our understanding of interstellar material. The object's compositional peculiarities, thermal activation patterns, and dynamical evolution enrich the growing catalogue of interstellar visitors, each of which broadens the spectrum of physical processes scientists must consider. As detection capabilities expand through missions such as the Vera C. Rubin Observatory and ESA's Euclid Survey, the frequency of interstellar object discoveries will increase, allowing comparative studies that place 3I Atlas within a broader population rather than treating it as an isolated anomaly. In summary, the natural object interpretation remains the most parsimonious and scientifically supported framework for understanding 3I Atlas. While uncertainties persist, as they inevitably do in astronomical research, nothing in the current dataset requires discarding established cometary physics. The object's chemical signatures, morphological ambiguity, thermal behaviour and dynamical evolution align with known processes governing volatile rich bodies exposed to solar radiation. Continued observation, particularly post-conjunction, will refine these interpretations, but the scientific foundation is robust. 3I Atlas is an unusual, intriguing and richly informative interstellar comet, not an engineered artifact. The anomalies it presents challenge models, not paradigms, and serve to deepen our understanding of the physical diversity of objects traversing interstellar space. As the inquiry into 3I Atlas advanced, the scientific focus shifted toward a deeper examination of the object's apparent morphology, specifically claims that it exhibits characteristics inconsistent with natural formation. These claims, centered on the perception of a rod-like body with aligned luminous nodes, demand a rigorous assessment grounded in the physics of imaging, the behavior of cometary surfaces, and the limitations inherent in observational reconstruction. Morphology, while often compelling to the human eye, is frequently the least reliable indicator of physical origin when derived from distant and low-resolution data. The human visual system is predisposed to discern order within noise. Pattern recognition, a cognitive adaptation essential to survival, predisposes observers to see structure where none exists. In astronomy, this effect is amplified by the interplay between faint signals and imperfect instruments. When images of 3I Atlas are filtered, enhanced, or compressed, particularly by non-specialists, noise patterns can be misinterpreted as coherent geometric configurations. This phenomenon became especially pronounced in the interpretation of certain leaked or amateur-processed frames where linear gradients, diffraction spikes, and deconvolution artifacts manifested as discrete luminous segments along a central axis. From a scientific standpoint, such features are readily attributable to the interaction of a small, unresolved nucleus, with the optical transfer function of telescopes operating near their sensitivity limits. When a point-like or slightly extended source saturates or approaches, saturation charge bleeding in the detector matrix can produce elongated streaks. If the telescope's support structure introduces diffraction, the resulting spikes can align with bright cores mimicking engineered patterns. Digital sharpening algorithms, particularly those employing aggressive noise reduction or contrast enhancement, can further exaggerate these illusions, transforming subtle gradients into apparent nodes. This does not imply that the underlying nucleus of 3I Atlas is structureless. Cometary nuclei are known to exhibit significant irregularities, with lobed shapes, ridges, fractures, and active vents distributed across their surfaces. Spacecraft imaging of comets such as 67P Churyumov-Gerasimenko and Tempel 1 revealed complex asymmetric bodies, unlike the smooth spheres imagined in early astronomy. If 3I Atlas possesses comparable complexity, its most active regions would naturally dominate the visible signal. In frames taken through narrowband filters that isolate specific atomic emissions, these regions could appear as distinct bright patches. Their alignment, if aligned at all, would be coincidental, a matter of rotation, viewing angle, and the positions of active vents. Rotation plays a significant role in perceived morphology. A rotating, irregular body experiencing anisotropic sublimation can display repeating brightness peaks as different regions rotate into sunlight. In low temporal resolution, imaging these peaks can blur into apparent stationary nodes, even though they originate from different surface patches. Without a well-constrained rotational light curve, attempts to infer shape from isolated frames remain speculative. Early photometric analyses of 3I Atlas suggest variability consistent with heterogeneous surface activity, yet the cadence and precision of available data remain insufficient to derive a definitive shape model. The presence of a smooth luminous sheath around the object in some images interpreted by non-specialists as evidence of internal illumination also has natural explanations. When dust particles scatter sunlight, they produce halos whose brightness is governed by grain size composition and scattering angle. Forward scattering, in particular, enhances brightness when the observer views the object at low phase angles relative to the sun. Under such conditions, even faint diffused dust envelopes can appear unusually bright and symmetric. This effect is well documented in cometry science and does not indicate the presence of artificial lighting or engineered radiators. Claims that evenly spaced luminous features resemble thrusters, radiator panels, or structural pylons arise largely from the misleading regularity imposed by image processing. Artificiality hypotheses often assume that true physical alignment corresponds to the observed pattern, yet the pattern itself may originate from the digital manipulation of a faint source. In reality, natural structures rarely produce perfect symmetry, while artifacts generated by detectors and processing pipelines frequently do. A symmetrical distribution of brightness in a heavily manipulated frame therefore argues more strongly for instrumental influence than for construction. Spectroscopic considerations further reinforce the natural interpretation. If luminous nodes were associated with propulsion systems or thermal management technologies, they would likely emit radiation in narrow, distinct bands not associated with cometry molecules. Thus far, all verified spectra of 3R Atlas show natural emissions, cyanide fluorescence nickel lines consistent with the breakdown of metal carbonyl compounds and broad dust continua. None display the monochromatic signatures expected from engineered systems. The absence of such features is a critical point, as spectroscopy provides far more reliable insight than morphology into the physical nature of distant objects. The distribution of dust and gas within the coma also provides context. Jets emanating from the sunward hemisphere, especially near perihelion, can create localized brightness enhancements that appear directional. Depending on the orientation of the nucleus and the flow of gas, these jets may focus material along narrow trajectories, forming conical or spindle-like shapes when viewed from Earth. These shapes can be mistaken for solid structures despite being made of particulate material flowing through space. Their appearance as defined forms arises from geometry illumination and viewing angle rather than material rigidity. Moreover, observational uncertainties near the Sun make faint structures susceptible to misinterpretation. Atmospheric turbulence affects solar-adjacent observations, disproportionately causing transient distortions. The combination of solar glare, chromatic aberration, and thermal gradients above observatories introduces fluctuations that can appear as structured shapes in short exposure or down-sampled imagery. When the Sun dominates the optical field, even small imperfections in focus or tracking can generate apparent linear or modular features. In this context, claims of rod-like morphology must be evaluated carefully. The limited resolution of available imagery ensures that no structure smaller than tens or hundreds of meters can be reliably resolved. Even if 3 Atlas possessed internal features, they would remain below the resolution of Earth-based instruments. Any appearance of detailed structure is therefore by definition an artifact of imaging, not a genuine surface reconstruction. This truth underscores the importance of relying on spectroscopy astrometry and thermal modelling over subjective visual impressions. In summary, the morphological anomalies associated with 3I Atlas arise naturally from a combination of optical physics, cometry activity image processing artifacts, and human pattern recognition. When examined within the broader scientific framework established in previous sections, these features do not provide evidence for artificial construction. Instead, they highlight the limitations of interpreting faint near-Sun objects through imperfect instruments and incomplete datasets. As the object emerges from conjunction and higher quality data become available, these interpretations will continue to converge on physically grounded explanations rather than speculative ones. As the morphological debate gradually settled into the domain of optical limitations and natural cometry processes, scientific attention expanded toward the broader question of trajectory and timing, 2 parameters that shape how unusual or expected an interstellar visitor appears. A trajectory is not merely a path through space. It is a historical record encoded in motion, preserving information about origin, perturbations, energy budget, and environmental interactions. For 3 Atlas, understanding its path into and through the solar system is therefore crucial to evaluating its nature. Interstellar objects arrive with an enormous diversity of approach vectors and velocities, shaped by distant gravitational encounters and the intrinsic kinematics of the galactic disk. Their arrival directions are expected to be isotropic, random, unconstrained, and without systematic alignment to any planetary plane. Yet 3I Atlas approaches the ecliptic plane at a shallow inclination, a fact that has attracted attention despite being scientifically unremarkable. The detection bias inherent in wide-field surveys makes discovery far more likely for objects passing near the ecliptic, where most survey telescopes concentrate their field coverage. In other words, observers preferentially discover interstellar objects whose trajectories coincidentally align with the paths that telescopes routinely scan. This observational selection effect significantly elevates the probability of finding ecliptic-aligned interstellar visitors, even if the true population has no such preference. Furthermore, the dynamical characteristics of 3I Atlas reflect a familiar profile, an unbound hyperbolic orbit with a modest excess velocity upon entering the solar system. The orbital energy is consistent with natural interstellar drift rather than accelerated propulsion. If propelled or altered artificially, the object's velocity relative to the local standard of rest would likely show directional coherence or energy levels inconsistent with gravitational influence alone. Yet its motion fits well within the distribution expected from bodies that have traversed interstellar distances over millions of years. The timing of the object's perihelion occurring during a solar conjunction relative to Earth has been labelled suspicious outside scientific circles. Scientifically, however, it follows straightforward orbital mechanics. For any object entering the inner solar system from specific quadrants of the sky conjunction is unavoidable at certain epochs. The orbital plane of Earth ensures that observers regularly lose access to objects passing behind the Sun, including many comets whose perihelia occur near the line of sight. Far from being indicative of intentional concealment conjunction, is simply a geometric consequence of relative positions in a heliocentric system. When assessing 3I Atlas's motion relative to the Sun, scientists focus on measurable model-constrained behaviour. These include minor perturbations caused by solar radiation, pressure, asymmetric outgassing, and potential fragmentation events. For objects with volatile-driven jets, non-gravitational accelerations can meaningfully shift the trajectory. Yet these shifts follow patterns. They scale with thermal input, correlate with rotational orientation, and vary gradually. The key scientific question is whether post-perihelion trajectory reconstructions reveal deviations that exceed plausible cometary behaviour. As of all pre-conjunction data, 3I Atlas remains firmly within the expected envelope for a natural object. A deeper scientific inquiry examines the object's path through the solar system and evaluates whether any coincidences arise from selection effects rather than intentionality. The relatively close passages to Venus and Mars, while intriguing at first glance, reflect the high density of planetary orbits within a narrow heliocentric annulus. A trajectory aligned toward the ecliptic has a high probability of passing near multiple planets, not because of targeted flybys, but because planetary orbits occupy that region of space. In statistical terms, such encounters are neither extraordinary nor suspicious. They illustrate the spatial realities of orbital architecture rather than an imposed guidance mechanism. Another dynamical consideration is the object's approach orientation relative to the Sun's radial direction. The inclination and argument of perihelion produce a path that enters the inner solar system at a moderate angle, consistent with dynamical models of natural interstellar bodies. These parameters do not reflect any recognizable optimization strategy that would enhance observational opportunities or minimize detection factors that might suggest intentional navigation. Instead, they reinforce the interpretation that 3I Atlas follows a typical natural path molded by gravity alone. The temporal clustering of certain reported anomalies, such as increasing brightness or changes in morphology, also aligns with expected perihelion evolution. Thermal flux increases dramatically as heliocentric distance decreases, driving more energetic sublimation and structural stress. Cometary nuclei often undergo fragmentation or localized activation during this phase, producing transient features and shifts in luminosity. Without continuous observation through conjunction, the precise temporal sequence of these events remains uncertain, but their qualitative pattern is entirely consistent with known cometary behaviour. A particularly important aspect of trajectory analysis is the sensitivity of orbital predictions to early measurement uncertainties. For interstellar objects, the limited observation arc before conjunction increases error margins. Astrometric uncertainties propagate through orbital solutions, meaning that small deviations from predicted positions post-conjunction may result from earlier measurement noise rather than physical forces. Scientists therefore distinguish between statistically significant orbital shifts and those attributable to initial uncertainties. Only the former would necessitate exploring explanations beyond natural outgassing models. The dynamical landscape of the solar system introduces further complexities. As 3I Atlas interacts with the Sun's gravitational well, its velocity increases sharply near perihelion, making precise tracking more difficult. Meanwhile, solar radiation influences the trajectories of dust particles emitted from the object, producing complex patterns that may superficially mimic directional maneuvers. Without high-cadence data through perihelion, distinguishing between jet-driven acceleration and solar radiation effects remains challenging. Nonetheless, both mechanisms fall squarely within the naturalistic framework of cometary evolution. Trajectory assessment must also consider the broader astrophysical context. Interstellar objects are expected to arrive from diverse stellar environments and undergo gravitational scattering within their origin systems. Their velocities reflect the cumulative influence of their birth migration and ejection processes. The arrival of 3 Atlas in 2025 does not signify anomalous timing, but fits within an emerging pattern of detection made possible by increasingly sensitive sky surveys. With each discovery, the scientific community builds a statistical foundation upon which to understand the distribution and frequency of interstellar bodies. Within this context, 3I Atlas stands as an early data point rather than an outlier. In sum, the trajectory and timing associated with 3 Atlas reinforce the natural interpretation supported by previous analyses. The object's approach vector, perihelion timing, velocity profile, and planetary encounters all align with expectations for an unbound interstellar comet. No aspect of its motion requires artificial explanations. Instead, its dynamics illustrate the rich interplay of gravity thermal physics and observational geometry that governs the passage of all small bodies through the inner solar system. As post-conjunction tracking resumes, scientists will refine the orbital model further, but the foundation remains clear. 3I Atlas follows the path of a natural wanderer shaped by cosmic processes rather than by deliberate design. As the dynamical context of 3I Atlas became clearer, scientific attention shifted toward an equally important dimension of the discussion: the provenance, reliability, and interpretation of the data itself. In modern astronomy, the integrity of a conclusion rests not only on the physical plausibility of an explanation, but also on the transparency and quality of the observation supporting it. Given the proliferation of digital imagery, social media dissemination, and anonymous claims, the distinction between verified scientific data and unvetted visual material has become increasingly critical for 3 Atlas. An object already constrained by limited observation windows, this distinction plays a decisive role in shaping public perception and scientific analysis. The earliest claims of anomalous structure originated not from observatories, but from a processed video clip circulated online attributed vaguely to a Japanese source, yet lacking metadata calibration files or consistent corroboration. In astronomy, the absence of such contextual information severely compromises evidentiary value. Authentic astronomical data typically include detailed acquisition parameters, timestamp exposure, duration pointing coordinates, filter specifications, instrument configuration, and atmospheric conditions for ground-based images. Without these, it is impossible to determine whether a frame represents a genuine observation, a misidentified target, or an artifact generated through manipulation. Furthermore, video compression common in social media uploads can introduce block patterns, pixel interpolation artifacts, and smoothing effects that distort faint astronomical signals. When such distortions occur near bright gradients or compact luminous regions, the result can resemble structured geometry or discrete luminous nodes. Scientific image processing employs careful calibration frames, darks, biases, flats to remove systematic noise. Unverified internet footage, by contrast, often compounds noise rather than eliminating it, making morphological interpretation unreliable. This contrast underscores why professional astronomers rely heavily on raw data formats, such as FITS files. These formats preserve the numerical integrity of pixel data and include headers containing the observational context. A true scientific leak would almost certainly emerge in such a format, as FITS is standard across the global observational community. The absence of any FITS-based corroboration for the alleged engineered-looking imagery argues strongly against its authenticity. By comparison, the amateur observation provided by the Solar Telescope operator, known publicly as Thiago Dobsonian Power, offers a contrasting model of responsible documentation. His shared frame included acquisition details, equipment specifications, and an unprocessed version of the data. These characteristics allow other observers to evaluate noise patterns, assess signal strength, and test whether the reported morphology can be reproduced independently. While the frame itself did not resolve structural details, it did confirm the presence of a compact bright feature at coordinates consistent with official ephemerides for 3I Atlas. This alignment supports the scientific validity of the observation, even as it highlights the limitations inherent in amateur solar-adjacent imaging. Yet even this verified dataset must be treated conservatively. Solar telescopes designed for high-contrast imaging of the solar corona operate under extreme illumination gradients. To avoid detector saturation, observers often employ narrow band filters, high gain, and rapid exposure cycles. These settings necessarily amplify sensor noise and reduce dynamic range. The presence of hot pixels, chromatic aberration, and transient seeing distortions is therefore expected. These instrumental signatures can mimic faint structures, particularly when observers attempt to extract detail using stacking or contrast enhancement. Thus, while Thiago's frame confirms brightness asymmetries, it cannot be treated as evidence of engineered morphology. Understanding why false patterns emerge in images requires a deeper appreciation of the physics of near-Sun imaging. When observing faint objects against a bright coronal background, the signal-to-noise ratio becomes extremely low. Photon-shot noise dominates, and even small thermal variations in the detector contribute significantly to apparent structural features. Moreover, the Sun introduces stray light artifacts through diffraction around the coronographic mask or the telescope aperture. These diffraction patterns can produce rings, spokes, or linear streaks that interact visually with the faint signal from a nearby object. In undersampled or compressed imagery, the blending of these patterns with the object's signal can fabricate a misleading impression of structure. This effect is compounded by the human cognitive bias known as pareidolia. In ambiguous visual environments, especially those containing faint scattered light, observers subconsciously impose structure symmetry and intent. This tendency is well documented in fields ranging from planetary geology to deep sky imaging. The face on Mars remains a canonical example. Low-resolution imagery created the illusion of an engineered construct that dissolved entirely when observed at higher resolution. The same principle applies to comets observed near the Sun, where resolution constraints and processing choices often shape perception more powerfully than underlying physical morphology. Beyond the challenges posed by image interpretation, the question of data withholding warrants scientific consideration. While some narratives frame the absence of high-resolution perihelion imagery as intentional suppression, the reality is far more mundane. Astronomical data pipelines are complex. Instruments undergo calibration cycles, and observational teams often retain proprietary access for time-limited periods to conduct initial analyses. Additionally, solar-adjacent observations place significant thermal constraints on space telescopes. Missions such as Hubble and JWST employ strict pointing restrictions to protect sensitive components from solar heating. If an object lies too close to the Sun, these telescopes simply cannot observe it. The lack of perihelion imagery is therefore a predictable consequence of engineering safeguards, not evidence of concealment. Moreover, some observatories prioritize instrument safety over opportunistic science. During conjunction windows, communication with planetary orbiters is disrupted by solar interference, and onboard cameras may be powered down or redirected. Even if an orbiter or solar probe had the geometric vantage point to observe 3I Atlas, its operational schedule and instrument protection constraints might prevent data collection. The absence of such observations must therefore be interpreted within this operational context. Scientists also emphasize the role of independent verification. For an extraordinary claim to gain traction, multiple observatories, preferably employing different detection modalities, must reproduce the result. No major observatory or solar mission has reported anomalous structure, propulsion signatures, or spectral inconsistencies. Instead, all verified data sources converge on a naturalistic profile, a diffuse coma with volatile-driven emissions, a trajectory consistent with gravity-dominated dynamics, and brightness variations explainable by thermal processes. Thus, while unverified images and speculative interpretations continue to circulate, the scientific foundation remains anchored in datasets obtained through transparent, reproducible methods. These datasets collectively reinforce the natural object interpretation and underscore the necessity of rigorous provenance when evaluating claims about interstellar objects. As the discourse surrounding 3 Atlas progressed, scientific inquiry began to concentrate on the natural mechanisms that could fully account for the object's observed properties. The goal was not to dismiss unconventional interpretations outright, but to test whether established cometary physics, thermodynamic principles, and spectral chemistry sufficiently explain the available data. This approach reflects the methodological foundation of astrophysics. Every anomaly must first be interrogated within the framework of known physical processes before invoking extraordinary alternatives. One of the central pillars of this natural framework is volatile-driven activity. Cometary nuclei consist of mixtures of ices dust and mineral grains whose sublimation is triggered by solar heating. The sublimation process is governed by temperature gradients across the nucleus, which in turn depend on illumination, rotation, and material composition. Through this lens, the behavior of 3I Atlas near perihelion becomes comprehensible. Solar radiation increases surface temperatures, releasing gas through pores, fractures, or structurally weakened zones. This releases inherently uneven thermal inertia and irregular mineral distribution ensure that some regions activate earlier or more intensely than others. Spectroscopic detections provide direct evidence supporting this mechanism. The presence of cyanide in the coma is a well-established cometary signature observed in both solar system comets and interstellar visitors such as 2I Borisov. More intriguing is the detection of atomic nickel without an accompanying strong iron signature. Although initially perceived as anomalous, this observation aligns with the chemistry of metal, carbonyls compounds that form under conditions involving carbon monoxide and nickel-rich grains. When exposed to ultraviolet radiation, these compounds dissociate, releasing nickel atoms into the coma. Their spectral signatures then emerge naturally without implying any artificial source or exotic process. In this way, the spectroscopic profile of 3I Atlas, unusual though it may appear, remains consistent with thermochemical processes expected for an object arriving from a distinct stellar environment. The coma morphology also fits squarely within natural interpretations. The so-called sunward jet, which some viewed as suggestive of engineered propulsion, is better understood as a projection effect. When a jet originates from the sunlit hemisphere of the nucleus where thermal activation is strongest, it can appear to extend toward the sun even though the gas flows away from the nucleus. This effect has been documented extensively with notable examples in comets displaying pronounced anti-tails. These apparent sunward extensions are governed by the orientation of dust streams relative to the observer. The persistence of such a structure in 3I Atlas therefore strengthens rather than weakens the cometary interpretations, indicating a stable sun facing active region. Another natural feature of interest is the absence of a large, well-defined dust tail in certain images. Cometary tails form from dust expelled by gas jets, accelerated by solar radiation pressure. If the dust grains ejected by 3I Atlas are larger or denser than typical, they may respond weakly to radiation pressure, resulting in a short or diffuse tail. Alternatively, the coma may be dominated by gas emission rather than dust scattering, especially if the object's composition is unusually rich in volatile species. Such compositional differences are plausible for interstellar objects formed under conditions distinct from the protoplanetary environment that shaped our solar system. Thus, the reduced visibility of a tail does not challenge the natural object model. It simply reflects the diversity of physical properties across interstellar bodies. Comet fragmentation is another phenomenon capable of producing transient structures that, when observed under suboptimal conditions, appear anomalous. As objects approach perihelion, thermal stress can induce cracking, exposing fresh layers of volatile material and triggering sudden outbursts. These events produce asymmetric comae, discrete bright patches or transient plumes that may resemble structural nodes in processed imagery. Fragmentation has been documented in objects ranging from sun-grazing comets to more distant bodies such as 67P, whose surface evolution was recorded extensively by spacecraft. If 3I Atlas experienced even minor structural stress, the resulting features could readily account for observations that seemed at odds with a single uniform nucleus. The challenge then lies not in explaining the anomalies, but in distinguishing between physical features and observational limitations. Instrumental noise, atmospheric distortion, and low signal strength can all generate spurious signatures. For example, detector blooming, a phenomenon where bright pixels saturate and spill charge into adjacent columns, can produce linear structures misinterpreted as rigid components. Similarly, when observers apply noise reduction or sharpening algorithms to faint data, they inadvertently impose artificial patterns. These processing-induced artifacts often mimic regular spacing or symmetry, amplifying the human tendency to infer intentional design. A further consideration is the behavior of interstellar comets across different wavelengths. Observations in infrared, ultraviolet, and visible bands each emphasize different components of the coma and nucleus. A region that appears bright in one wavelength range may vanish in another, depending on whether the emission originates from gas fluorescence, dust scattering, or thermal radiation. Without a multi-wavelength dataset currently limited by conjunction constraints, interpretations based solely on narrow observational slices risk overemphasizing isolated features. The natural explanation also extends to rotational dynamics. Cometary rotation induces periodic brightness variations that can produce misleading visual impressions in short-duration imagery. If active regions on the surface rotate in and out of sunlight, apparent nodes of brightness may emerge in specific rotational phases. Such nodes would not represent structural elements but rather the same surface patches periodically illuminated under changing angles. The absence of clear periodicity in available photometric data is not surprising given the limited temporal resolution and noise levels. However, the lack of stable repeating bright spots argues against the presence of fixed artificial features. Ultimately, the question of natural versus artificial origin cannot rest on morphology alone. Scientific evaluation prioritizes spectral evidence, thermal modeling, and dynamical behavior. In all these domains, 3I Atlas aligns with expectations for an interstellar comet. Its chemistry has plausible natural origins. Its coma morphology reflects projection effects, volatile-driven jets, and dust physics, and its brightness evolution follows known thermal activation patterns. While the object remains scientifically compelling, owing to its unusual composition, interstellar provenance, and perihelion timing, none of these characteristics require invoking non-natural explanations. In this sense, the emerging scientific consensus frames 3I Atlas not as an anomaly demanding radical interpretation, but as a valuable data point in the expanding field of interstellar astronomy. It demonstrates that interstellar objects like stars and planets exhibit diversity shaped by their unique formation environments. As observational technologies advance, objects like 3 Atlas will help refine our understanding of chemical evolution across the galaxy. Anomalies become opportunities, irregularities become clues, and even when the data challenge our models, they do so within the robust, predictable framework of natural physics. As the scientific dialogue surrounding 3I Atlas matures, it is increasingly clear that the object's significance extends beyond questions of morphology or origin. Whether ordinary or unusual in its physical properties, 3I Atlas represents a valuable opportunity to study the broader processes governing interstellar material and the dynamic interactions between such bodies and the solar environment. In this final analytical segment, the emphasis shifts from defending the natural object interpretation to exploring what 3i Atlas can teach us about planetary system diversity, the chemistry of distant stellar environments, and the methodologies required to refine our understanding of interstellar visitors. Interstellar objects provide unique windows into the conditions of other planetary systems, conditions that cannot be recreated in terrestrial laboratories or inferred solely from remote sensing of exoplanets. Their compositions reflect the chemical inventories of their birth environments, while their surfaces record the accumulated effects of radiation exposure and collisional histories across interstellar time. For 3i Atlas, the detection of volatile species such as cyanide and atomic nickel suggests a lineage shaped by carbon-rich and metal-bearing materials. These signatures hint at a protoplanetary environment rich in carbon monoxide and other molecules that lead to the formation of carbonyl complexes. Such environments are not rare in the galaxy, but are challenging to study directly. The presence of these compounds in 3i Atlas therefore provides evidence for chemical pathways that may occur widely across stellar nurseries. The object's thermal response near perihelion also offers insight into the physical properties of interstellar nuclei. The rate at which 3i Atlas brightened prior to conjunction suggests a moderate level of surface activity, likely influenced by a layered structure of ices with varying sublimation thresholds. Interstellar exposure tends to deplete more volatile species over time, yet deeper layers may preserve trapped materials that activate only under strong solar heating. Observing how these layers respond as the nucleus approaches and recedes from perihelion helps constrain models of heat conduction, volatile retention, and structural integrity in long-travelled bodies. Even the absence of catastrophic fragmentation, if confirmed, would provide valuable constraints on mechanical strength and cohesive forces in interstellar material. Another important scientific dimension relates to the growing diversity of interstellar objects. Prior to 2017, none had been definitively identified. In just a few years, Vlad Oumuamua and Tuai Borisov expanded the category to include one object with an unusually elongated shape and no detectable coma, and another with a classical cometary appearance and active gas release. 3 Atlas appears to fall closer to the second category, though with its own distinctive chemical and morphological profile. This expanding sample illustrates that interstellar objects like comets and asteroids within the solar system occupy a spectrum of physical characteristics. Diversity rather than uniformity may be the defining feature of this population. The implications extend planetary system evolution. Many interstellar objects are believed to be ejected during the early stages of planetary formation, when gravitational interactions between protoplanets and debris disks scatter material into interstellar space. The physical and chemical properties of those ejected bodies therefore encode information about the processes operating in distant systems. For example, a high abundance of carbon monoxide ice in 3i Atlas could reflect colder formation zones or specific disk chemistries. The detection of metal-bearing volatiles suggests interactions between mineral grains and carbon-rich gases during early accretion. These characteristics help refine models of disk chemistry across the galaxy. Another lesson concerns observational challenges. The case of 3 Atlas demonstrates how conjunction windows data scarcity and low signal-to-noise conditions complicate interpretation. For future interstellar visitors, preparing for rapid response observations across multiple wavelengths will be critical. Missions capable of ultraviolet spectroscopy, infrared thermal mapping, and high-resolution imaging could collectively capture the full physical evolution of a fast-moving interstellar body before observational gaps occur. The conjunction of 3 Atlas highlights the need for coordinated global strategies to ensure that solar-adjacent geometries do not produce avoidable data loss. Equally important is the role of data handling and computational modelling. The case underscores why scientific conclusions must rest on calibrated datasets rather than speculative imagery. As detection rates increase, robust automated pipelines will be essential for distinguishing genuine anomalies from noise artifacts. High-precision orbital modelling incorporating both gravitational and non-gravitational forces will improve trajectory predictions and enable earlier identification of objects exhibiting unusual dynamical behaviour. advanced thermophysical modelling will refine predictions of sublimation, rotational states, and fragmentation probabilities. Together, these tools will enhance the scientific return from every interstellar encounter. Perhaps the most profound scientific implication of 3i Atlas is the recognition that anomalous observations do not necessarily point to extraterrestrial engineering, but may instead expand the known limits of natural diversity. Many early interpretations of Oumuamua framed its behaviour as incompatible with natural processes, yet continued research produced plausible explanations rooted in physics. The lesson here is methodological. When confronted with unfamiliar data, the scientific response is to broaden the range of natural models before introducing extraordinary hypotheses. In the case of 3i Atlas, this approach has proven effective. Features initially described as artificial linear morphology, discrete brightness patches, unusual spectral lines have found coherent explanations within a strengthened understanding of cometary physics and interstellar chemistry. In broader astrophysical terms, objects like 3i Atlas help bridge the gap between planetary science and galactic astronomy. They serve as material messengers carrying fragments of distant systems into proximity where detailed analysis becomes possible. As observational capabilities improve through facilities such as the Vera Rubin Observatory, ESA's Euclid mission, and future infrared space telescopes, the discovery of interstellar objects will likely become routine rather than exceptional. With each new visitor, scientists will refine models of chemical diversity, volatile retention, and dynamical evolution across the interstellar medium. Thus, the lasting value of 3i Atlas will not be found in speculative claims about artificiality, but in its contribution to a rapidly maturing scientific field. Its passage through the solar system, though partially obscured by conjunction, provides data that enrich our understanding of how planetary systems form, evolve, and disperse material. It underscores the importance of rigorous methodology, highlights the limitations of low-fidelity imagery, and affirms the predictive power of cometary physics. Even as its origin remains an object of fascination, its behaviour falls comfortably within the natural processes that shape icy bodies across cosmic distances. In this sense, 3i Atlas exemplifies the scientific value of interstellar visitors not as mysteries designed to provoke extraordinary interpretations, but as natural artifacts whose complexity invites deeper study. Each new observation strengthens the empirical foundation upon which models of interstellar chemistry and dynamics are built, and as our tools and frameworks continue to evolve, so too will our capacity to interpret the next interstellar traveller, not with speculation, but with a refined understanding shaped by the lessons of those that came before. Traveller, our journey drifts now toward its quiet ending as we leave 3i Atlas, suspended in the bright silence near the Sun. Soon, when it emerges from solar conjunction, telescopes across Earth will return to their vigil, comparing predicted paths to measured ones, examining spectra for unfamiliar notes, and listening for the faintest hint of something that does not belong to a comet at all. But tonight we pause inside the uncertainty, letting the not knowing become a gentle place to rest. Whatever 3i Atlas proves to be an interstellar wanderer with unusual chemistry, or a messenger from a deeper architecture of the cosmos, it reminds us that the universe is vast, patient, and still unfolding around us. Our small act of observing becomes a quiet conversation with creation, a way of saying that wonder still matters, that curiosity is still stronger than fear. Thank you, observer, for drifting through this mystery, for listening to the sky with openness instead of urgency. The story is not finished. The data is still travelling toward us, still being shaped by forces older than any human memory. But for now, in this calm space between questions and answers, allow yourself to rest beneath the unresolved stars. Stay curious, traveller. Rest well. The universe will keep watch, and if this story found you tonight, you are welcome to return for the next.